So here's actually a bunch of images of CCDs. This is standing for charge coupled device. This one's ours. So this is our Proline, whatever it's called. It's got like a barcode. Anyway, it's a Proline CCD. It's PL16803. I did not remember that. I looked it up. And it's 4096 by 49, oops, there's a 6 there, sorry, by 4096 pixels. It's a pretty nice CCD. Each of the pixels is 9 microns in size. You can find all of these numbers on the web, by the way. So the total chip, I did the sums, it's 37 by 37 millimeters, so the thing's tiny, right? So this whole big box, you've all seen the box, right? A lot of this has to do with the cooling system, I think. And the CCD itself is just a little tiny chip. And here's a picture of it, presumably inside that circle. We're not going to open it to look at it because we want to keep it nice and sealed in there. Okay. You know, this is a nice CCD. This is a nice, it's a nice CCD, but it's the type of CCD that, you know, amateurs, very well-off amateurs who are very into astronomy sometimes buy. It's not a professional grade CCD. I've put some pictures here of some of the sort of famous CCDs in astronomy. This one's actually the SDSS. So this was actually built in around about 1990. So this is a long time ago now, actually, right? It's currently in the Smithsonian. It's being held as an artifact of scientific importance, which I think is pretty cool. The colorful stripes that you see are the filters. So instead of a filter wheel, this one had fixed filters over parts of the CCD. And they imaged by kind of gradually going across the sky. I looked up the numbers. It was actually 30 CCDs, but each of them was only 2048 by 2048 pixels. So each of them is a quarter the size of the one we have now, which I think tells you something about how CCD technology has changed in the last 20 years. Yeah, so composite CCDs are actually pretty common in astronomy. So if we kind of go forward in time, which way around is it? Yeah, this one. This is DE cam, the dark energy camera that actually went on the telescope at CTIO down in Chile that we talked about. This is actually 62 CCDs, and they're not square, they're rectangular. So these ones are 2048 by 4096. The numbers are always, for whatever reason, it's 4096, 2048, 1024, 896, whatever that set of numbers is. There's a name for that set of numbers. But that's how CCDs get built. And then this last one I have as an example, this is actually the LSST, or the Vera Rubin Observatory camera. And this is the biggest one that exists right now. This is a total 189 CCDs, each of which are the same size as ours, so 4096 by 4096. And the reason you do this, the reason you go for a really big CCD is basically to be able to image large areas of the sky, right? So it's really what it's for. So how does the CCD actually work? It's an application of the photoelectric effect. So this is just the effect that when photons are incident on metal, they release electrons. So that in itself is pretty straightforward, right? You know, your photons fall onto silicon and they release electrons, you're done. The trick with the CCD is we want the electrons to remain in a pixel. So we want to somehow capture them and like leave them there for a period of time. And then we want to read them out in an array. And so you can get these diagrams that show you how this is done, but basically little charges are used to kind of keep the electrons where they are in this array of pixels while you're collecting data. And so while you're collecting data, light is incident on your CCD and it continues to release electrons, hopefully in proportion to the number of photons that land on it, and they stay where they are while you're collecting the data. So I guess we have to trap the electrons in these little sort of buckets, the buckets that we call pixels. And you can't really see, but if you have like a microscopic view of a CCD, you can start to see the granularity. You can start to see these little pixels that are kind of almost etched, I think, on the surface. The Howell book has a whole section on the manufacture of CCDs. It's a little out of date now, but it's still kind of interesting to see like the different techniques they used for manufacturing them. Okay, this diagram is also from the Howell book to talk about how CCDs are read out. And this is the reason, if you, I don't know if you've noticed when you've been observing, but you do the exposure and then it stops, and then there's a little bit of time before you can do the next exposure, right? It's not instantaneous. And this is kind of the reason why that is. So this is a 3x3 CCD, right? That is being modeled as a little sort of set of rain buckets. So the rain is supposed to be electrons. And actually it's photons that rain down really, right? And they release electrons. So the analogy breaks a bit, but here we've got rain just falling on our buckets. So our buckets fill up with water. And if it was raining in some weird pattern, you could measure the pattern, right? So you could measure the distribution. How are you going to read it out? Well, what happens is that basically only this, I guess this is a 3x4 CCD, only this channel gets read out, and it gets read out one at a time. So you measure how much water is in this bucket by tipping it into here, and then you tip it out, and then you measure how much there is in this bucket, and so on. And then you do the next column. So then this whole thing gets dumped into here, and you do it again. And then this whole thing gets dumped into here, and you do it again. Older CCDs would take quite a long time to do this. So one of the things CCD manufacturers will kind of advertise is how quickly you can read out their CCD. We will get to reasons why, but you want this process to be very accurate, right? You want the loss of water, the spilling of the bucket, to be very small, but it's not zero. So you will find that there's a little pattern that you get across the CCD from readout, and there's a little bit of noise that gets introduced called readout noise. So you call this sequential readout. There's a bunch of options in the CCD. You can just expose a part of it, or you can bin. So you can do 4x4 binning before you read out. All of those things make the readout quicker. So if you're going to do something where you want to be really quick, like imaging a bright star that's changing in brightness, for example, which you might want to do for transit photometry, you might want to just do the bit around the bright star. Okay, I think the next one's just a little GIF showing this in a bit more like how they do it. Sort of they manipulate the charges so the electrons move around, and the accuracy, or the transfer accuracy, has to be very high. So it's something like 99.99, I don't even know, but like some very high proportion of the electrons get shifted accurately. I think the numbers are in one of the books, so you can look them up if you like. But if you think about our CCD is 4096 by 4096, right? So we're not just doing 3 readout, we're doing 4096 shifts and then 1, and then 4096. So we do 4096 by 4096 shifts, right? So it's even a tiny inaccuracy in each shift. It's going to kind of multiply and cause problems. So this is done incredibly accurately. It's really impressive that it can be done. So a little bit more about technology and kind of the terminology. Our CCD is a front illuminated CCD. So a lot of professional, or the CCD on the LSST telescope, or professional grade CCDs are backlit. So this is this side, or back illuminated. What the difference is that the sort of the electronics and the bits that cause the shift register, if the light is incoming on them, the electrons are all there, right there. Whereas in this sort of backlit thing, you have to make the wafer much thinner, and then these kind of shift it along the thin wafer. We are slightly reaching the limits, as you could probably tell, of my understanding of CCD technology. However, what I do know is that this way, the backlit way, is way more sensitive, but way more expensive because it's way harder to build. The front lit way is slightly less sensitive. So if you're building a $1 billion telescope, you might want to not be cheap on your CCD. But it's cheaper to build this way. And so for the kind of level that we can afford as a small college, this was perfect. Quantum efficiency is a fancy name. Effectively means the proportion of photons that cause a response. So I think it's actually, well, it's either expressed as a percent or a fraction. So, you know, the light that's falling into your telescope, some fraction of it will get through the optical path through, you know, bounce around off the mirrors and all that kind of stuff. And then, you know, what then on top of that is the fraction of the photons that reach the CCD and make a response. And so this is the quantum efficiency for our CCD that the manufacturers report. So you can see across the optical wavelengths from like 400 to kind of 700 nanometers is optical. We have quantum efficiency in the range of 40 to 60%. And then, you know, over here in the infrared, it starts to drop down. I wanted to look up what the quantum efficiency was of, like, you know, the LSST camera, since I told you the chips are way more light sensitive. And so this orange line on this curve from this paper, Coles et al., is the LSST. And so it's going up to like almost more than 90% in places. So it is significantly more efficient than our CCD, or the claims that our CCD make. Up to almost 100% efficient here in the long wavelength. And if you're curious, they also put the human eye. So our eyes are pretty inefficient relative to CCDs. And some other detectors. So I guess it has the Sloan CCD on here as well. So this was that 1990s CCD. Pretty nice camera still. Our eye is most efficient right around the peak of the sun's emission. I don't think that's a coincidence. It probably is slightly a coincidence that our CCD peaks there, because you could pick different materials that have different response to electrons with different energies, right? But this has all to do with the sort of transmission of the window into the CCD and the response of the metal to photons incident on it, and lots of details that I don't want to get into really. Okay.
Does it mean that we should adjust the exposure time based on the quantum efficiency at different wavelengths?
Well, I mean, it should tell you, right, that that I band filter is less sensitive than the sort of G band or the R band. But there's also a factor in there, it's the spectrum of the source you're looking at. So a lot of stars are brighter, right, in this part as well, but some are going to be brighter in the infrared. So the answer to that is it kind of depends. The Sloan imaging, I'm really familiar with SDSS imaging, right? So Sloan has UGRIZ. Everyone defaults to R because it's right in the center of the CCD sensitivity, and it's also where the filter has the best transmission. The U and the Z band, we don't have those two filters, and there's a reason for that, is that their transmission through them was really rubbish. So those are like way lower sensitivity imaging from Sloan. So most people just do GRI because those were the sort of three middle ones, and those are the three filters that Paul decided we should get, and he was quite right. Those were the right ones to choose. I wanted to talk about plate scale. And so here was where we can also talk a little bit about focus, right? So we want the CCD to be at the focal point of the telescope. And I promised a diagram about why a filter would change that. But if you have, I'm going to draw a lens. If you have a lens that's focusing at a certain point, and then you put a filter in there. I should use a color. I should totally use a color for filter. So we put our filter in there. That's going to bend the light very slightly. So you might end up with a slightly more distant focal point. or a slightly nearer focal point, and so you might need to adjust the focus. And you know, when you're adjusting the focus, physically what you're doing, the microfocuser is physically moving something inside the camera so that the CCD is at the focal point. And the bulk focuser, so this is our focus on the computer, moving this end, and that coarse focus knob is moving the primary mirror. That's why you need to do it slowly, because it's moving a big bit of metal. It needs to settle. Okay, so that is focus and the focal point. And now let's talk about the focal plane. So now we want to know like how big something is on the CCD chip. So like what 1 pixel is on the sky, like how big is 1 pixel? There's actually 2 concepts that you'll read about. You'll hear about plate scale. And this is a concept really from photography. It's like how much of the sky is going to be projected onto your entire imaging area. By convention, use the diagonal size of the chip. And if you think about it, you can convince yourself that if the distance between the mirror and the focal point, that's going to be your focal length, that's your F. If the triangle's that way around, what's basically going to happen is something of scale very, very small, so we're going to ignore the size of it here, is going to be projected out to an angle. This angle theta is going to be the angular scale of something size d in the focal plane. Okay, so remember back to ASTRH341 or 205, we're going to always basically use a small angle approximation, right? So theta, which is the plate scale, is just going to be that linear size of the plate. So in this case, it's going to be the diagonal size of the chip. So it's going to be, let's say, the diagonal size of the chip divided by the focal length of the telescope. For the full angular size of the chip. So I looked at these numbers for our telescope. The diagonal size of the chip, according to the technical specs I found, is 52.1 millimeters, which now I'm saying it out loud is different from what I told you about 37 by 37, or maybe that's okay because it's the diagonal. So it's probably okay. And the focal length of the telescope, remember we talked about how it's a 16-inch telescope and it's an f10, and what that means is the focal length is 10 times the diameter. So it's 160 inches. So I'm not going to make you do all of the unit, some lovely unit conversions in there, because that will give you the angular scale in radians. So then you have to convert it to something that is sort of more astronomically understood. And it turns out this is 44 arc minutes. So I told you it's about 30 by 30, the square. So 44 is the diagonal, it's about right. Okay, that's the plate scale. So the pixel scale is going to be hopefully pretty obvious what the pixel scale is going to be, often little p. It's the size of the pixel divided by the focal length of the telescope. So again, I looked this up. The pixel size on our camera is 9 microns divided by 160 inches. We do a bunch of unit conversions, and now we're going to turn this into something in arc seconds. And actually turns out that the pixel, each pixel we have is 0.45 arc seconds. Which is lovely pixel scale to have actually. So the seeing probably was sort of atmospheric seeing here. It's probably 1 to 2 arc seconds, probably at absolute best 1 arc second. And so we're going to end up with a little basically square of pixels sampling our seeing disk, probably a little bit more than 2 by 2. And that's perfect for various reasons, but that's a lovely sampling of the PSF. So we'll get nice little circles. Right, you don't want your pixels to be too big compared to the seeing, because then circles won't look circular anymore. They will look pixelated. Any questions so far?
I'm just curious, like how good does seeing get if like around here is like 1?
I bet it doesn't ever get any better than 1.
Yeah. Okay.
I've not measured it. We can measure it from.
Oh, I meant like in other like in places
Oh,
where, like
on
observing.
the ground, I've 0.6 arc seconds at the top of mountains with very, very nice stable atmospheres, usually because they're on the coast somewhere. So like the beautiful Chilean observatories right on the Pacific coast.
Mhm.
I've heard about 0.6 arc seconds, but and then there's all kinds of games you can play to try to like correct for atmospheric turbulence to get better. So adaptive optics and stuff, but I mean, their fundamental limit, you'll remember, right? 1.22 lambda over d. We're nowhere near that on the ground, even with a 16-inch telescope.
Mm.
Yeah. So I think we'll save the rest of stuff about CCDs for next week.